Chapter 8, Practice Exam number 9. Above a well, a bucket of mass 2.1 kilograms is attached to a rope that is wound around the outside of a cylinder, and I give the equation for moment of inertia for a cylinder of radius quarter meter. When the bucket is allowed to fall from rest, it falls 10.5 meters in 2.1 seconds. I want to know the mass of the cylinder. So there's two ways to do it. This video is for using rotational dynamics to solve this problem. So in rotational dynamics, we're going to set up an equation for net torque and net force, one on the rotational thing, one on the linear thing. So the linear thing, we've got a bucket. The bucket has a mass of 2.1 kilograms, and it has its own force of gravity pulling on it, which in this case is 2.1 times 9.8, or 20.58. I'm not going to round that because we'll need as little rounding error as possible later. And the tension in the rope on the bucket will be pulling up. And that's it. I'm going to go ahead and say that since this bucket is only going to fall, I'm going to go ahead and make down positive and up negative. Okay. Then I write the Newton's second law, net force equals ma, for this bucket. So the net force in this case would be 20.58, there we go, minus t equals mass times acceleration. What is the acceleration, you may ask? To find the acceleration, we have to do a little bit of kinematics. So I said that this thing falls 10.5 meters in 2.1 seconds. Okay, so it's going to fall 10.5, yeah, 10.5 meters in 2.1 seconds, starting from rest. Okay, this doesn't look like much, but it is enough to do a little kinematics, assuming that I start at a position of 0. I can use this equation. Remember that one? Yeah, of course you do. I can use the equation to solve for A. This is 0, that is 0. So 10.5 meters will equal 1/2 A times 2.1 squared. If I do all that and solve for A, I end up with A is looking 4.76 meters per second squared. I'm going to store that in my calculator, however, and use it as an unrounded figure because it is not a final answer, it is an intermediate answer. So just store that. Store that, baby. Okay. That means I can go back up here and say 20.58. Whoop, 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 whoop. Did you see that? Glitched. Okay. Equals m, which I also know. Sorry, m is 2.1. Should have put that on the previous line. Times 4.6. The only thing I don't know here is t, which means I can just solve for it. So the tension is gonna be, looking for it, 10.58 newtons. Okay. We're just going to have that sit there for a little bit, and we're going to go back and look at the, cylinder. Okay, so, I did a different color for this one. For the cylinder, the only thing pulling on it is the tension, and it's pulling at a distance of r from the center of the cylinder. So I can write the net torque on this cylinder is going to equal the moment of inertia of this cylinder times the angular acceleration of this cylinder, which angular acceleration is the same thing as linear acceleration over r. So I'm going to replace this with that. Okay, I can do that. Alrighty, so I need to make the direction that this would spin match the way that the bucket would fall. So I said when the bucket falls down, that's the positive direction. When the bucket pulls down, it would cause this thing to rotate clockwise. So clockwise must be the positive direction. I know that's against our normal conventions, but this is what we're going to go with. So on the net torque side, there is only one torque, and that torque is the force T times the distance from the pivot at which it was applied, which is R. It would cause it to turn in the positive direction, so this is a positive torque, and it makes a right angle, so there is no sign. So the left-hand side is simply TR. Okay, then I've got I. Well, the I for a cylinder is 1/2 mr squared, using a capital M here where capital M is the pulley, not the bucket. The bucket was a lowercase m. And then I've got A over R. Okay, well right away I've got some stuff I can cancel. For instance, this R on bottom cancels one of the R's on top, so that's going to get rid of my square. But then I've got an R on the left and an R on the right, so those are going to cancel. Turns out the R doesn't matter. That's kind of weird, but it happens. So now I've got this simplified equation. The tension in the rope should equal 1/2 m times linear acceleration of the bucket. Okay. I want m, so I'm going to solve for m, multiply both sides by 2, divide by a, should get me m. So that's going to be 2 times 10.58. There we go. Over a, and I stored that, so here's where you pull it back out again. If I do this with the stored in the calculator, the mass ends up being, where is it? 4.44 kilograms. Okay, so that gets us an answer. Let's talk about points. Okay, so Newton's second law, both linear and rotational, are kind of the biggie for this one. So I need at least a point for each, although I'm tempted to do more. In fact, yeah, let's do more. It's 2 points for each of them. Oop, there we go. This is Newton's second law linear, Newton's second law rotational. You get a point for some arrow showing that either A equals alpha times R or alpha equals A over R. You can just do it by a direct substitution like this, or you could have written it out somewhere. But somehow the relationship between linear acceleration and angular acceleration is a point. Okay, so that's 5 points right there. Somewhere you're going to have to use kinematics, so choosing an equation is a point, and getting the intermediate answer of acceleration is a point. Okay, so that's 5, 6, 7. Then putting the correct thing on the left-hand side, like doing the forces correctly, is a point. Make sure it's like showing that it matches your directions and stuff. So that brings me up to 8, I think. 3, 4, 5, 6, 7, 8. Stop it. No. Okay, and then a point for the answer and a point for units. Makes 10. Again, this is only one way to solve this problem. There is another video floating around of how to solve this with energy conservation.